All right. Now, in terms of rate, there's a lot of things that can affect the rate of a reaction. The nature of the reactants, what kind of reactants are sort of reacting, their sort of physical state. Small molecules tend to react faster than larger ones. Gases tend to react faster than liquids, and liquids react faster than solids. And that's just think about the energy aspect of it. Obviously, gases are flying around with a lot of energy, which means they're more apt to come in contact with each other and start reacting. Liquids still have a little bit more energy, obviously, than solids. So that's going to allow it to react a lot easier. Solids are pretty much your lowest in energy, so they're just kind of sitting there. So they're not going to react as much or as fast, probably, than a liquid or a gas. But there are certain solids that react faster than others. Powdered solids react faster typically than block solids. And that's more surface area for the reactants to happen. Maybe some of you experienced that with like the magnesium, for example. As I mentioned before, when you're coiling that magnesium, that last experiment we did, if you coil it really, really tight, it doesn't allow a lot of surface area, obviously, for that solid to react with the HCl, and it's going to react a lot slower than if you coiled it in a sense where a lot more of the magnesium, for example, was available to the HCl. It would probably react a lot faster. When we talk about there are certain metals that are, for example, more reactive than others. That activity series of metals that we talked about, that is essentially where you have all the elements, hydrogen sort of in the middle, bunch of other elements. Remember, anybody sort of higher on the activity series will react with somebody lower. Anybody lower on the activity series will not react with anybody higher. We saw that with really single replacement reactions where somebody was coming in and trying to kick out another element. Ions also react a lot faster than molecules because, frankly, where you find ions pretty much is in solutions, and they are floating around, which means they're good to go. They're ready to react. You know, nothing else has to happen for them to be good to go. They are, by nature, just good to go. Temperature is an overwhelming type of factor in terms of reaction rates and how fast, for example, or how slow, for example, a reaction may take place. Increasing the temperature typically will increase the reaction rate. It gives everybody a lot more energy. And there's really kind of two major things that are needed for a reaction to take place. Things need to hit each other, and they need to hit each other with the right amount of energy. So at a higher temperature, you're going to have a greater proportion of molecules, for example, with sufficient amount of energy for that reaction basically to take place. There's an actual relationship and equation that relates temperature to the rate constant that we'll see a little bit later on in this chapter here. Catalyst is another thing that can affect the rate of a reaction. I think we talked a little bit about catalyst along the way here, but again, a reminder that a catalyst is not a reactant. It is not a product, and it does not get used up. In the reaction. It is there simply to facilitate, in most cases, the reaction happening a lot faster. There are some catalysts that actually slow down the reaction. Those are sometimes referred to as negative catalysts, but I would say 99.9 times of the time, probably if somebody is talking about a catalyst, they're referring to it in the sense of it being something that will speed up a chemical reaction. Catalysts are kind of like mixtures as well. They can be homogeneous catalysts, which means that the catalyst and what is reacting are all in the same phase. So a very common sort of catalyst that's used are acids as catalysts, and acids can react really well as a solution with other solutions to help facilitate the reaction occurring. Heterogeneous catalysts are ones that are in different phases. So a lot of catalysts are metals, for example, and things that are reacting, say, are gases. And a lot of times you will find the catalyst written on top of the arrow. So maybe you'll see something like platinum written, maybe H+, which is an acid catalyst. And a lot of times the catalysts are listed usually on top of the arrow to indicate that they are there to sort of facilitate the reaction happening faster, but not really a reactant or product, which is why they're usually placed on top of the arrow. Also, concentration is a really good factor as well. Typically, if we have a larger concentration, there is a greater frequency of molecules able to react. And when we think about molarity, for example, the true definition is moles of solute over liters of solution. And when we talk about molarity, which is a solution, basically, there is the solute and the solvent that make up that solution. And out of those two, it is always the solute that's really the thing that's reacting. And that's because that's also the name of the solution. So if you have a 6 molar hydrochloric acid solution, hydrochloric acid is the solute, and that's really what's reacting. The water part of it, which is the solvent, is not really doing anything. It's really that sort of concentration of the solute. And that means that if you have a larger concentration, you will have a lot more solute present in the solution. More solute present means greater chance of everybody come together a lot quicker and faster and more efficiently. And that will also result usually in a faster rate. Gases also depend on the partial pressures. As we know, higher pressure typically means you have a higher concentration of gases. And that also would allow you to have things reacting a lot faster. In addition, at a higher pressure, you usually have a smaller volume, which means everybody will be near each other, a lot closer to each other. This is going to encourage sort of collisions and reactions to occur. So let's talk a little bit about the rate law and the relationship of what it looks like and how we sort of calculate it. The rate law, as I mentioned, is a relationship that's used a lot in kinetics. And one of the couple of things that we see in the rate law, which is one for like this. This is the rate law for the expression or the reaction above it. The rate is equal to K times the concentration of A to the X and B to the Y. Once again, that is our rate, which is our molarity over seconds. That is our rate constant. These are our concentrations of our reactants. And X and Y, in this case, are what are referred to as the orders. And X in this case is the order with respect to A, and Y is the order with respect to B. And one of the important things that you see with the rate law is it's all about reactants only. So unlike the rate expression where we sort of relate everybody in the reaction, the rate law only deals with reactants. X and Y are the orders, and it is always found experimentally. So usually the rate law is always found experimentally, which means typically you will get like tables and you'll have to do some calculations to figure out what X and Y is. X and Y is not, in the case of the rate law, it is not the coefficients in the balance equation. So we do not use the coefficients as the exponents here. You actually have to look at the experimental data to sort of calculate those things. So what is X and Y in the orders? You could think of it as kind of like the proportion of X and Y that's necessary to be mixed together to produce a reaction at a specific rate. And why would it be important, for example, to know, what the orders are and what the rate law is for a particular reaction? So let's just say, hypothetically speaking, we calculated the rate law for this guy, and we found that the order for X and Y was 1 each. So the rate law would be, in this case, if it was 1 and 1 for each of those, would be the rate equal to K times concentration of A times concentration of B. By the way, the overall order of the reaction can be found by adding those individual ones together. So in this particular case, most of the time we don't write ones, but these are going to be ones here. So the overall order in this case is going to be 1 plus 1 is second order. So this would be a second order overall reaction by adding those together. And that also is important for, again, for selection of correct sort of equations and relationships as well. So why is this important? Let's just say we did this reaction and we started with a concentration of A of 2 molar and a concentration of B of 2 molar in this particular case. So we did, say, our first reaction at those two concentrations. If we were to sort of stick it into this equation, that would give us basically the rate is equal to basically 2 times 2, and that would give us like 4 molar seconds, for example. I'm not going to worry about the K because it's a constant, so it'll be the same as long as the temperature and all that stays the same. It's going to be a constant value, but that will be really the same sort of value. Now, let's just say that you did this reaction and you found it to be way too fast, for example, for you to take measurements. And this happens sometimes when you are doing an experiment and you mix things together. And if you're like taking all day to get it into the machine, the reaction in some cases can be over before you actually get into the machine to take your measurements. There are reactions that are like super fast. They kick off really fast. And by the time you get there, you're actually catching like the end of the sort of reaction, not the entire sort of reaction. So you go, well, that's not good. I want to slow it up, maybe. I want to slow this reaction up. So let's just say, okay, in this case, I want to run A at 2 molar, but I'm going to cut the concentration of B in half to 1 molar. And if I put this into my rate law here, that would give me, again, the rate is equal to, in this case, basically 2 times 1. And that would now take us down to an average rate of 2 molar seconds. I cut the concentration of B in half here. The resulting rate also got cut in half, right? By doing that. So this is a way I could slow it down, right? If I wanted to speed it up, maybe I would, concentration of A is 2 molar. Maybe I bump up B to 4 molar. Now when I put it in here, I have K 2 times 4 gives me 8 molar seconds. I increased, right, the concentration of B in this case, doubled it, and that actually doubled the rate. So maybe the reaction was too slow for what you wanted it. You wanted to speed it up. You can play with the concentrations, and it would have an effect on the rate. Now, in this case, would it matter which one I did that to? In this case, it wouldn't. Although I changed B in this case, I could have just changed A, and it would have resulted in the same sort of relationship because the orders of both of those guys are basically 1 each. Now, let's say we did an experiment and we found that the rate law for this reaction was K, A to the first order and B to the second order. And in this reaction, the overall reaction would be 1 plus 2, which would be a third order reaction by adding those sort of exponents together. Now, let's just say we started with the exact same concentration that we did here in number 1. And in this case, that would give us that the rate is equal to K times 2 and 2 squared. So that is 4 times 2. That's basically giving me 8 molar seconds. In this particular case, because the order of B is actually second order, even though we started with the same concentration as the one on the right for each of those guys, we actually have twice the starting initial rate, right? So this reaction out of the gate is going to be twice as fast as the previous reaction that we did on the right-hand side. We will also see a greater change in what happens if we did the same thing there, where we cut the concentration of B in half. So if we did that the same way and we cut it in half, we would have 2 times 1 squared. That's going to give me 2 molar seconds. In this case, I cut the concentration in half of B. My rate actually went down by a factor there of 4, right? So it went from 8 to 2. So it slowed down significantly, right? In this particular case. Now, in this case, though, if I did the concentration of A and cut that in half and left my other guy initially at 2, we would actually get 4 molar seconds. So in this case, there is a difference if you did A versus B, right? If I only cut A in half, my rate only dropped half, right? It only went down to 4 versus all the way down to 2 in this case. So by knowing these orders, knowing the rate law, if you needed to in a real life situation, sort of figure out, I need to kind of speed up this reaction, I need to slow down this reaction. There are certain reactants that will have, obviously, in some cases, a greater effect on the overall rate by playing with their concentrations than others. Now, what happens if I did a rate law where I ended up with A to the 1 and B to the 0? When you take something to the 0 power, what does it equal? It equals 1, right? Which basically means that equals 1. Which means in this particular reaction, If I change the concentration of B, will it have any effect on the rate? It will not, because it will always just end up being the same one no matter what number you throw in there. You can increase it like tenfold, it will still end up being one, right? Because it's to the zero order. The only thing that would affect this reaction is actually A. So if you had a rate law for a reaction that you were working with like that, and you wanted to affect the rate, either make it faster or slower, your only option in that case would be you have to do something to A to kind of speed it up or slow it down, because you can do whatever you want to be, it will not affect it. Any questions on that there? So how do we calculate? As I mentioned, rate laws are typically calculated from experimental information. So typically you will be given a table such as this, and typically in this table, there are the concentrations of your reactants. There's also the initial rates, and there's usually a number of different experiments that were performed. So you could do it one of two ways. You can either look at the relationships in the table and figure out how things are changing, how the concentration is changing, their rates are changing to each other. But most people have a difficult time sort of doing that. So I find mathematical approach is probably the better approach for it. So you can use this relationship that the rate of 2 is equal to K A to the X, B to the Y, divided by rate 1 is K A to the X and B to the Y. So the rate 2 and rate 1 here doesn't mean you just go to the table, take the first and second entry. It means that you go to this table, and in this particular table here, there's only 3 entries. You could have ones that have 4, 5, 6, a ton of entries in the table. But what you are looking for is, in this particular case, 2 entries where one of the reactants concentration stays constant and the other one varies. And if you have 3 reactants, you would want one where 2 of the concentrations stay the same and one varies. The idea here is to have only one variable, which makes mathematically easier to solve, right? We have multiple variables, not so good. So if we wanted to do that, for example, if we look at this reaction, our generic rate law would be the rate is equal to K times F2 to the X and ClO2 to the Y. So our goal from this table is to try to figure out what each of those values basically represent. So to do that, I'm going to go to the table, and I can see that in experiment 1 and 2, the concentration of F2 stays the same. So I'm going to start with that. I'm going to look at experiment 1 and 2. And when I look at experiment 1 and 2, just to give you prettier numbers, usually when you do this calculation, you typically want to take the one where the rate value is the larger number and put that on top. So if you take the one that has the larger rate and put all that information up on top, that will usually give you a lot more whole numbers than decimal numbers. So a lot of times that's easier for people to kind of see what the end result is going to be. So what I'm going to do is, because number 2 is the larger rate, I'm going to put all of that up here, up on top. So all of that information for experiment 2 will go up here. That means we have 4.8 times 10 to the minus 3 is equal to K times our concentration of A, which is 0.1 molar to the X, and for our B, 0.04 molar to the Y. So everything that I put up on top is all the information for experiment 2. So basically, you don't want to mix and match here. So all the way across here is everything that went up there. Now I'm going to put everything for experiment 1 here on the bottom. And to do that there, that's going to give me 1.2 times 10 to the minus 3 molar seconds. K, our 0.1 molar squared, and our 0.01 there molar to the Y in this particular case. And what we're going to do now is just some math. So if I take 4.8 times 10 to the minus 3 and divide it by 1.2 times 10 to the minus 3, that is going to give me a 4. When I come to this side, that is the rate constant, and that is a rate constant. And the name is rate constant, which means it's the same number. Although I don't know what it is at this point, it should cancel out because it's the same number. When I come to my concentrations that are the same, these x's are also going to be the same number. I don't know what it is at this point, but I do know that they should cancel out. Now, when I come over here, that's basically 0.04 divided by 0.01 gives me 4 to the y in this case, basically. Any questions on that there? You could probably clearly see that y in this case is going to equal 1. By the way, if you didn't have a pretty number, you take the natural log of 4, or the natural log of 4 brings the y down, divide the natural log of 4 to both sides. It's one way to get rid of it, and you will end up with 1. So if you don't have really pretty numbers, take the natural log of both sides and divide it out. That will get you there. So what that tells us is the order with respect to ClO2 is going to be 1. Now that we did that, we want to go back to our table, and we want to find 2 entries where the ClO2 is going to remain constant and the other one will vary. And in that case, it looks like experiments 1 and 3 will do that. That will keep those guys constant. So experiment 1 and 3. We're going to do the same thing. I'm going to go with this guy up on top because that's the larger rate. That will give me 2.4 times 10 to the minus 3 molar seconds equals K, 0.2 to the X, 0.01 to the Y. We're going to put everything from experiment 1 on the bottom, 1.2 times 10 to the minus 3 molar seconds. K, 0.1 molar to the X, 0.01 molar to the Y. Once again, we're going to do some math here. That's going to give us a 2. These K's should cancel. When we do the next guy, that's going to give us a 2 to the X, and these guys should also cancel. And here we can see that X is equal to 1 in this case as well. Any questions on that? What we just did is use the experimental information to figure out the orders. That means that the rate law for this reaction would be K is equal to F2 times ClO2. The overall order in this case for this reaction will be 1 plus 1, which is a second order reaction. Any questions up to that point? Once we found the actual completed rate law and actually have the orders for everybody, we then can use the completed rate law to actually calculate the value of the rate constant. So in this case, I'm going to solve for the rate constant, and that would be K is equal to the rate divided by the concentration of F2 and ClO2. Basically, I'm taking these guys and dividing it to the other side, along with his proper orders. Obviously, in this case, both of the orders are 1, but if there was like a 2, we would need to keep the square with it and all that. Where do we find this information? You could then go back to your table, and you could actually choose any entry you like. You could choose number 1, you could choose number 2, you could choose number 3. Just can't mix and match. You got to choose one and use them all. So for me, I'm going to use the first entry, which means the first rate there is 1.2 times 10 to the minus 3 molar seconds, divided by the concentration of my first reactant and the concentration of my second reactant. That is going to give me a rate constant in this case of 1.2 to the minus 3 divided by 0.1 and divided by 0.01. Going to give me 1.2 units. Molarity on top will cancel. Molarity on the bottom will cancel. Still leaves us 1 over molar seconds, which, by the way, are the typical units that you find for a second order reaction for the rate constant. So this is a very common sort of problem that you need to know how to do. You can take the table. You want to find 2 entries where one stays the same and one varies. And you could use that to figure out the orders. Once you figure out the orders, then you could go and figure out the rate constant. Once again, if I put the values in for experiment 2 or experiment 3 here, I will end up with the same rate constant. It should end up with the same value no matter which one that you choose. Any question on any of those there? So as we see there, they are always determined experimentally, our rate laws. It's always in terms of the reactants, no products. And once again, in the rate law, the coefficients are not where we get the orders from. You do have to sort of use the experimental information to find it. All right, so why don't we try one here, see what you come up with. Determine the rate law for this one with the orders. And what is the overall order? And what is the value of the rate constant? So take a few moments, see what you come up with using this information. Okay, let's take a look to get into the end here. Once again, we can start with kind of the generic rate law, which will be the rate in this case is equal to K. Remember, it is only our reactants involved. So our first reactant, we could call it to the X. And our second reactant, we could call for the Y. Remember, we're going to use this table basically to figure out those orders. And when we do so, we want to look for two entries where one stays the same and one varies. And again, this case here, since we only have two reactants, that's what we're looking for. Again, if you had multiple reactants, you want to just only have one variable. So experiments 1 and 2 keeps that first guy constant there. So putting in our values, I'm going to choose experiment 1 here because it has the larger rate to put up on top. So again, I'm just going to put everything from experiment 1 up on top. And again, we're just going to kind of fill in our normal sort of thing here. For experiment 2, we're going to put everything on the bottom there. X 0.017 to the Y. Once again, we're just going to do the math. So that should give us a 2. Once again, the rate constant on top and bottom should be the same number, although we don't know what it is at this point. The order here for both these x's should be the same, although we don't know what it is at this point. That should cancel all that out. And once again, here we will have our guy there, which should give us a 2 to the y. And once again, here our y will equal 1. Any questions on where any of those numbers came from? Now that we did it for the first reactant and kept constant, we want to go back to our table and find two entries where we keep the other guy constant. And in this case, it does look like experiment 2 and 3 will do that for us in this case. We'll keep those two guys constant. So we'll look at experiment 2 and 3. Once again, I'm going to choose the one with the larger rate and put it up on top. So that's going to be experiment 3 for me. 4.4 times 10 to the minus 4 molar seconds equals our K, 0.16 molar to the X, 0.017 to the Y. I'm going to then put everything from experiment 2 on the bottom, 1.1 times 10 to the minus 4 molar seconds, K, 0.08 to the X, and 0.017 to the Y, which we're keeping constant. Here doing our math, we're going to get a 4 is equal to, again, our K's will cancel. That's going to give us a 2 to the X. And again, this guy is going to cancel. In this case, you could also probably easily see that X in this case is actually going to equal 2, our second order with respect to that guy. Any questions on that? Now that we have that, we could actually write our completed rate law, which is the rate is equal to K times our S2082 minus, that was to the second order, X, and our I minus to our first order. That would be our completed rate law with the orders. The overall rate of this reaction would be just adding those orders together. So 2 plus 1 would give us a third order reaction in this particular case. Any questions on that? Now we can solve for K because we have the orders. So, excuse me, K in this case, rearranging this, we're going to take all these guys to the other side, is going to give us the rate is divided by S2082 minus, once again, we do need to square it, times our I minus. And again, at this point, we could choose any entry in the table to find this. I'm just going to choose entry number 1, and that will give me 2.2 times 10 to the minus 4 molar seconds divided by 0.08 molar squared and 0.034 molar. And when it's all said and done there, we will end up with 2.2 to the minus 4 divided by 0.08 squared and divided by 0.034. Looks like 1.01. Unit-wise, molarity up on top will cancel one of the molarities on the bottom, but we will still have 1 over molar squared seconds, which, by the way, if you count up the letters, is 3 letters, and it's a third order reaction, right? Just like we counted the one last time, 1 over molar seconds is 2 letters, which is a second order reaction. 1 over reciprocal seconds, or 1 over seconds are reciprocal seconds, 1 unit, first order. So a lot of times the number of letters you have will equal the overall order of the reaction as well. Any questions on any of those steps there? All right, we lay it up there